right. We're good? Cool. All right, so I can talk like a human now, which is nice for me, but told I'm still supposed to stay quiet for a few more days, so we're gonna have one more mic'd class, and then we'll just have like normal professor stuff after that, which will be a relief. Yep, so welcome back. Nice to see you guys. So let's see here. In terms of 837 stuff, your next assignment is due probably Wednesday. Is that right? Cool, great. And then after that, you have one more? Huh. And your final projects. And as usual, I should remind you that your final project proposal is due the same week of your midterm. And you've been reminded of that about 10,000 times. So now you know. Any procedural questions? Anything I'm forgetting today? I think it's pretty easy. Cool. I look forward to seeing lots of you guys in my office hours because it's the every other week scenario. Okay, so right, we're going to continue. Now that we have our basic machinery for rendering, right? We have the ray tracing algorithm. We're now going to kind of dive into a few specialized topics that have to do with rendering because we have the basic algorithm down, right? So we talked about texture mapping and we talked about materials. Another key kind of special topic that shows up not just in ray tracing, but just generally in graphics, now that we have a rendering algorithm, is sampling, aliasing, and mipmaps. Just out of curiosity, how many of you guys have taken some kind of class that has the Fourier transform in it? Yeah, fair number. This is nice because MIT. But even if you haven't, so every year I get budgeted one lecture to teach sampling and reconstruction without Fourier. And every year we experiment with different strategies, and every year it fails. So today is that day, and we have yet another approach, and we'll see how it goes. Essentially, our goal here, you're going to see things like integrals today. I apologize. I know that they're threatening, but we're going to kind of do a very schematic picture of the sampling reconstruction world and articulating how it's relevant to graphics. You could easily teach an entire course. In fact, there are entire courses in the EE side of our department that cover this story in a lot of detail. Obviously, we're not going to do that today, but you're going to get a couple kind of key messages about how to implement your ray tracer in a way that takes care of that nasty little set of jagged edges that we've seen in our pixels so far. Okay, that's basically the goal at the end of the day here. And along the way, we're going to learn a nice story about Fourier and companies. Right, so today's warning is this is experimental. Every year I put up this warning. Every year I lose about 2/3 of the students within 82 seconds of the beginning of lecture, but we're going to give it another shot and see how it goes. All right, this is painful for me, by the way, because my background is in math, and I would love to just like do this on the board, but that wouldn't be a great use of your time. So here's the 90 miles away perspective, is that we've quietly been sweeping a bunch of kind of related issues under the rug in 837 so far, right? Like for instance, here we've made our typical balls on checkerboard motif that we enjoy in the ray tracing world so much. And of course, when we render our images, we see this very typical artifact, right? This is the jaggies or staircasing artifact that's appearing anytime you have a sharp boundary between two shapes, right? And as we've already talked about, the basic reason for this issue is that what am I doing by ray tracing algorithm? I'm like maybe shooting a ray right down the middle of the pixel, reading off the color, but like if I'd perturbed that ray a little bit within that square, I might have gotten a different color. And somehow we haven't accounted for that, right? And so we talked a couple lectures ago about some heuristic ways we might fix that, right? Like shoot a bunch of rays inside of that pixel and average the color that you get as a result. But it turns out there's a very, very deep sort of theoretical story that's sitting underneath, like, well, where do I send those rays? Are they uniform inside of this square? Or are they like kind of concentrated toward the middle? Like what should I do there? And it turns out that although this is a subtle decision, it's one that you really have to get right, and that a lot of literature in computer graphics world is dedicated to. And this issue just keeps reappearing in slightly different contexts each time, right? So this issue we've seen, right, this has to do with sampling inside of every pixel. A related one that we talked about when we talked about texture processing was the fact that, like, if I'm rendering, Helen, she's all the way in the back of the room, and I have this extremely detailed texture of her skin, then probably with two adjacent pixels, when I render them, I do my texture lookup, they're very far apart in the texture map, right? And essentially, at that point, your color is just random, right? Because there's all of this oscillation between, the white shiny parts and the less white parts on this texture here that are just getting neglected because of essentially undersampling. Or yet another one, if you played with MS Paint, is this idea of jaggies, right? I'd really like to draw that diagonal line, but of course, if my pixel grid is this coarse thing that's sitting underneath it, then the best I can do are these blue squares, which somehow don't look so great. So these are the artifacts we've already talked about, and indeed, these are artifacts that show up everywhere in your everyday life, anytime you interact with a piece of digital equipment, right? So like another good example is something called moire patterns. Like if you take an old, probably now your iPhone's camera is high enough resolution that this doesn't happen, but certainly with some of the older cameras where there were fewer pixels, if you took a photo of a brick wall, notice that there are like these kind of low frequency striping artifacts that are hiding inside of there. And again, like in some sense, what's going on? You have this very repetitive pattern, which is roughly at the scale of the distance between two pixels, and something is going wrong. Right? That's kind of where we're at. And by the way, it's not just pixels, it can also be in time, right? So if you guys have watched car ads, actually I think in car ads sometimes they'll go back and they'll post-process to get rid of this effect. But if they don't, then you're getting what looks like what we call the wagon wheel effect, which my cursor is not making easy to target. Here we are. Yep, so here's a car. For a little while it looks like the wheels are moving forward, and then suddenly, if you look at the hubcaps, I mean, there's sort of one of two options, right? Either somebody's got some really crazy hubcaps, or there's something that's going wrong with the camera, right? And probably you guys can explain what's going on here, right? Your camera maybe is sampling frames at like, about 1/30th of a second. Your wheel is turning not quite 360 degrees in that 30th of a second. So then by the time you snap that next frame in your video, it looks like it moved backward, whereas the reality is it moved all the way around and just didn't quite close up the loop. Right? And so this, again, we call this the wagon wheel effect, but it's just another example where somehow there's something happening very quickly, in this case in time instead of in space, and it's leading to an undesirable artifact. Right? Although I think for whatever reason, our brains are like kind of okay with this artifact more so than some of the rendering ones. Yeah?
So for the artifact that you had when it was like the brick wall, and you had like this, right?
Yeah, it's called moire pattern. Let me see if I can get it back.
Yeah. So I feel like whenever I take a picture of my computer screen,
Uh-huh.
I have like a similar artifact. Is that related?
Yes, it's exactly the same artifact, right? Your computer screen is composed of this very dense little grid of pixels. Yeah. And somehow the spacing of those is interacting with the spacing of the sensors that's inside of your camera. Yeah. So this is called a moire pattern, right? This low frequency artifact, which is appearing in a high frequency image. And of course, this is a really pernicious beast, right? Because if you're talking about your typical kind of noise filtering, this doesn't look like noise. It looks like a low frequency kind of smooth thing on your image. So it's very hard to get rid of it a posteriori. And so this is just an issue that shows up everywhere, right? And from my perspective, essentially what's going wrong is that we all live in, arguably, unless you're, I guess if you're in the previous class, maybe you disagree, but ignoring quantum effects, we roughly live in a real valued world, right? There's a very complicated scene here. But yeah, we're making discrete measurements, right? Like your photograph that you're taking is this big discrete array of colors. And the reality is that like hiding inside of every one of these pixels, right, is quite a bit of information, right? And so if I put this image grid on top of this complicated photograph and ask you what color is this pixel, I don't think it's so clear. But hopefully it will be at the end of lecture today. Incidentally, one thing to note is that this isn't just a digital issue. I mean, if you look in the inside of your eyeball, which I realize is kind of challenging task, then you'll see that indeed your eye also has a big discrete grid of sensors. And indeed later, we're going to talk about perception in this class. We'll see that essentially a lot of these crazy kind of visual artifacts or optical illusions are basically leveraging the fact that your eye, for example, has uneven sampling rates of color versus black and white, which can lead to some really bizarre things that in our case, probably your brain kind of accounts for after the fact. Okay, so this is the basic broken issue, is that like, we're asking an awful lot of our ray tracer, right? Which is that hiding inside of every pixel here is a lot of information. Again, I think I told you guys about like when I was at Pixar and they had these scenes in Finding Nemo, like all the artists got really excited about modeling aquatic life, and then like the side effect was that in every pixel there's like 100 little swaying plants in the background of the scene, and then rendering became insanely expensive, right? Because you have to somehow account for all of that information just to decide on like one color at one point, which seems like a lot. Everybody get our story so far? I think it's intuitive what goes wrong. The problem is that the fix to this little bug is like the tip of a ginormous iceberg worth about an entire graduate degree worth of mathematics. Okay, but from about 50 miles away, our strategy is pretty simple. It's that we're going to use some combination of mathematical and perceptual tricks to compensate for these sampling issues. Right? So sampling issue, otherwise known as aliasing, is essentially any time that you have some real valued object and you're just collecting its value at sort of discrete points. Right? That's exactly what's going on in our ray tracer. And we're going to have two ways of fixing it. One is to compensate for sampling mathematically, to kind of revisit what it is that we're doing in the rendering pipeline and see if we can explain that behavior and come up with better methodologies that somehow choose that pixel color in a smarter way. And the other one is just to say like, well, okay, some artifacts your eyes notice, some artifacts your eyes don't. Right? So for instance, like white noise style artifacts, sometimes your brain will just smooth out. And so if we can replace, for example, that smooth moire pattern, like what we were asking about before, with white speckly noise, like, okay, neither one of those is great, but it might be perceptually that the latter one is better. And this is kind of the fun thing about computer graphics, right? On the one hand, you have algorithmic knobs you can turn. On the other hand, you can leverage the fact that your client is somebody's eyeball, and you put these two things together, and that's what matters for formulating your algorithm. Incidentally, does anybody know what aliasing stands for? It's thematic this week. Come on, it was even a TV show, right? I think it was called Alias. It's a ghost, right? And it's Halloween this week because right? Because you're seeing this signal which isn't really in your image, but somehow is triggering something because of the way that you did your sampling. We'll explain this in greater detail further on. And there are many examples. I mean, you can do these for days, and some of them are kind of fun to look at. Right? Here's another with a bowl of fruit. Here's sort of an explanation of your jagged boundaries, right? So here are your sample points, and you can see, for example, in this pixel, I just had bad luck, right? There's some orange in there, and I just didn't see it. And by the way, this isn't just a subtle effect, like a one pixel difference. So for instance, here is an evilly drawn image where I have very slivery triangles, but they just barely miss the sample points, right? And so the end result is a pretty drastic change to the image when you render it. Or here's another kind of dramatic one, which is sort of the typical test case that you see in this literature, which is a checkerboard floor moving into the distance. It's very dramatic. And you can see these moire patterns going in all kinds of funny ways in the background here. There's your photography example. Okay, so there's some philosophical points here, right? I mean, the reality is that we are now just tiptoeing into the interaction between physics and math, right? And the reality is that, although we're going to talk a lot about mathematical models, of course, it's just a model. And in some sense, this is a great example of why I really like graphics discipline a lot, because somehow we're taking continuous real valued problems and translating them into these discrete kind of computational things. It's very different from like algorithms class where you've got discrete input and discrete output. Right? Here your input is like, light rays. And really, in some sense, this is what we do in this entire course, right? I mean, when we talk about ODEs, what did we do? We took time and we discretized it into, discrete samples. And when we do ray tracing, we send out discrete rays of light instead of continua. And really, the key here is careful mathematical understanding. Okay, enough of that. So let's do a little bit of like this much Fourier analysis. Okay, so let's start with our sort of modeling assumptions. Like, what's our starting point here? So first of all, you have to ask the question, which is, what is a pixel? And in our model, and again, it's a model. This is a model for how stuff works. Although it happens to be more or less how your computer screen works. We're going to think of a pixel not as like a box or a disk or like a tiny little light bulb sitting in your screen. By the way, for some reason, people think that that's how your screen works, but it's not. There's a light sitting on the side of your screen. But we're going to think of a pixel as a sample, like a dimensionless object. What that means is it's just like a little value of light that comes in at this point. So I know nothing about the neighborhood around this point. I just get one sample worth of information, right, at maybe the center of that little square. Okay? And basically what we're going to ask today are what is the consequences of taking this real value universe and then like putting little, basically covering my eye with a sheet and then putting little pinholes on a regular grid. Right? And if that's the only information I have, what can my brain infer about what happens in between? Right? That's the basic question you want to ask when you're talking about sampling and reconstruction. We've already used the word sampling a bunch, so let's fill in our definitions. Sampling is sort of mapping a continuous function to a discrete one. Right? Or a different way to think about it is just kind of collecting values of some continuous function at different locations. It's important to make a quick distinction between two different discrete phenomena that both happen in graphics, but we're going to address them separately in this class. So there's sampling, right, where I'm like looking out into the world, but the reality is that I'm like sending little probes out at discrete sets of points. There's a different issue, which is that my computer can only store so many numbers. Right? Like if I have a 32-bit color, then I have 2 to the 32 possible colors that I can represent on my computer screen. That is a different kind of artifact, right? So in other words, like I can't represent every possible shade of red in my RGB color, right? I can only do the ones that are in my my double precision floating point, right? And that style of artifact is known as quantization, which is taking a continuous value and mapping it to a discrete one. So let's take a look at a picture of sort of what the difference is. So if I have a function f of x and I talk about sampling, then what I do is I take a sequence of x values and I evaluate f of x at those points. Okay, that's what sampling is. Then quantization would be now I look at the y-axis and I have a sampling of y values and I say you could just have to round to the closest one. So we're going to just worry about the horizontal one. We are going to use real values in this direction. That's pretty realistic simply because typically these days in graphics we use floating point numbers with a way more digits of precision than your eye can see. At least if you do it carefully. We're going to talk about that later. Okay. So that's our basic model. Okay? We want to know what the effects are of going from the left-hand side to the right-hand side, ignoring quantization for now. Okay, so here's going to be our basic process we're going to analyze, which we're going to think of visual light as like a continuous function. In other words, like at every point in my image, x comma y, in theory, I could put in x comma y, and I guess the world would give me back the color at that point, right? Now I'm going to take my camera, I'm going to put it in front of my eye, and then I'm going to sample f at a grid worth of points. Or maybe I do that with my ray tracer. It's going to turn out, the theory doesn't really care where that comes from. And that gives me a finite list of numbers. That's the thing we can store on our computer. And now the question is, let's say I have the best display in the world. I can take that list of numbers and I can do anything that I want to produce a square worth of colors. Right? So maybe I have a super high resolution screen, whatever, all sitting inside of that little square. The question is, what is the best that I can do to approximate that continuous function just given that set of discrete samples? Right? Because that's somehow the lower bound in the behavior of these graphics tools. Upper bound, rather. And what we're going to see is that both sampling and reconstruction can cause problems. In other words, when I sample, I think that's the obvious one, right? Like I throw away data in between these little points of light. But when I reconstruct, in other words, like when I use my CRT and display those pixel colors in a particular way, I can introduce additional errors. Right? I think this is pretty reasonable. And the main issue that's going to come into play is the density of your samples. Right? So here actually is a pictorial example showing what that moire pattern that you saw in the brick building, where that comes from. So here is a very high frequency kind of sine wave. And I've sampled it at these dotted lines, which are obviously spaced much farther apart than the what do you call it? What's 1 over frequency? Wavelength. Thank you. Obviously, the distance between these dotted lines is much larger than the wavelength of this sine wave here, right? And the red dots are what happens when I sample. And the really amazing thing, which is 100% true for sampling sine waves at weird irregular intervals, is that they too trace out some other sine wave, but the frequency is lower. And that is exactly the artifact that we saw in that previous image. Okay, and that's called aliasing. And the basic point here is that this can happen any time that the spacing between these dotted lines is bigger than about 1 wiggle worth of information. And that's what we're going to aim to Formalize is the wrong word in this class, but we're going to aim to pictorially kind of sketch out why that would be the case. Cool? Cool. All right. So how are we going to solve this in practice? Well, you only got so many options, right? One is usually just blur stuff out. Like you'd prefer to not have any signal there than to have bad low frequency signal that shouldn't be there. Or we're going to oversample, meaning we're going to send a lot of rays into a single pixel, in effect overcoming that little spacing bound, and then average it out so that at the very least we get rid of that kind of low frequency artifact that we saw before. This is the same trick, by the way. If you go over and take an audio class, you'll see that it's exactly the same stuff they do there. It's just that in their universe it's one-dimensional, ours it's 2 or 3. Yeah? And so in order to really understand that, we're going to need a little bit of math. Okay, so let's do that. And here's our big warning. Like we're going to do like the opposite of rigorous. We're not going to talk about Lebesgue whatever measures in this class. We're going to just draw pictures with abandon and pretend like everything is finite dimensional. Okay, so for now, our model is going to be just one-dimensional. So we're going to forget the two-dimensional image grid for now, and we're going to think of just like maybe one row of an image like that. And the green plot here is like the true distribution of light. Okay, so this is some function that we want to approximate. And we'll call this, if you're in the know, you call this like a signal, right? This is a one-dimensional signal as a function of x. Okay, so what's going to be our model for sampling? So we have this function here. And now, essentially, all we're going to be able to do is to collect the value of our function at some regular spaced out set of points. So the fancy term for that in Fourier analysis is that we're going to say we multiply our function by an impulse train, which I think would be a cute name for a band. But essentially, the idea here is that I'm going to cook up a function which is 0, like literally just zeroes out this green thing at a bunch of places except at this regular set of intervals. If you're in the know, the things that are regularly spaced out are delta functions. If you don't like that, it's actually kind of okay to think about like a function which is like 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. Right? So if you multiply those two things together, essentially I'm throwing away all of the information between the red arrows. Because that's what my ray tracer does, right? Like this is where I threw out my rays, and what I got back was the height of this arrow, and everywhere else I just don't know anything at all. It could be that there's something crazy here, I just don't even know. I'm going to keep repeating this concept, and I want you to keep it in your head. Okay, so what does that mean? After I ran my ray tracer, really the information I got was not this green thing. In fact, I have no clue what happens between those samples. All I know is this, right? I just get rid of that green background. So that's the sampling process, to replace that green function with this red guy. And now, what do? Well, the reconstruction takes as input these red values, and its job as output is to produce some purple thing that interpolates the red information. Right? That's what reconstruction is doing. And what does it know? It knows just the red values and the spacing between the samples. Okay. So what's the big problem here? Well, let's take the green function and the purple function and put them together. And what do we get? Well, we got that they don't agree. Right? In particular, they more or less agree when this function is moving slowly, but then there's this little wiggle that's hiding down here. And because that wiggle is contained within these two red samples, we just don't observe it, and the purple function smooths them out. And that is our basic issue with aliasing. And the key observation to make here is that this is high frequency information. Namely, this wiggle happened very rapidly relative to the spacing of the red samples, and that's what's causing this particular issue. So here's a more obvious example, right? Here's a really crazy green function with even fewer red samples, right? So probably if I reconstruct, I'll get something like that, which obviously is not a very good approximation. Cool. So the question that we want to ask is, under what conditions do we think that we can more or less close this loop? In other words, I collect those samples, and then I reconstruct, and I get more or less the image that I started with. And under what conditions do I get a schematic that looks kind of like this one? Okay. And indeed, the worst possible example happens with sine waves, right? Where, here at the blue points, we collected samples from the red sine wave. Then when we reconstructed, we got something that looks like a coherent signal. The only problem is it's completely wrong. Okay, so if you get nothing out of today's lecture, other than this, I think the simple message is that when sampling falls apart is because the function wiggled too much in between two consecutive samples. And that is information that we just threw away. We just don't know it. And so now we need some way to formalize that story, right? And once we formalize and put a little math there, then that'll actually give us a few clues on how we can improve our reconstruction in practice. So let's do that. Right, so here is the closest we're going to get to math, which is due to a gentleman named Joseph Fourier. He's an interesting guy. You know, if you take a math history class, there's a problem, which is like mathematicians just have really boring lives. Like they just mostly hang out, they have kids, you know, whatever. Fourier and Galois are like the two mathematicians that did anything interesting. And right, Fourier was like out in, I think he was in Egypt, right, with the French army. But in any event, the basic idea of Fourier theory, which by the way was not accepted at the time of Fourier, it was just kind of like, he didn't write it down in a formal way, and the French mathematicians are kind of picky, so they dismissed it a little bit. By the way, it still happens today to some of us that do mathematical research. But in any event, Fourier's big observation was that you can take any function, any signal, where for suitable definitions of any, and write them as sums of a bunch of sines and cosines, a bunch of little wiggly objects. And this is going to give us the information that we need to tell stories about sampling, reconstruction, and a million other things. Yeah? In case you guys aren't familiar with Fourier theory, you probably have seen a Taylor series. And that's a very similar story, right? So what do you do in a Taylor series? You take a function, in that case an analytic one, and you replace it with a sum of monomials, right? You write it on the monomial basis. It kind of sounds like our second lecture in this class. Here, all we're going to do is replace the monomial basis with the new basis, which is sine of kx. And then the question is, what are the sort of consequences of using that basis? That's basically all Fourier theory. It's just another change. It's just another basis to add to your list that we already have in this class. Okay. So the basic kind of schematic here that Fourier started to work out was an object called the Fourier transform, which I'm guessing many of you have seen before. And the basic picture to have in mind is that you start with some function where x is like position, right? So like think of this like your rendered image, right? So f of x is like the color at a point x. What we're going to do is we're now going to generate a new function called the Fourier transform of f, which instead of taking an image, takes in a frequency, like the spacing between two wiggles on my image. And what it gives me is the amount of that frequency that is in my original function. And we're going to formalize that in a second. So first of all, well, the sort of beautiful observation from Fourier, which we're not going to cover in this class, is that this is invertible, that like I can take the Fourier transform of something and I can undo it. In other words, the frequency information is all the information I need to describe a function. Which is not obvious, by the way. That's why he's kind of a big deal, that one. So the question becomes, how do I measure frequency content? And the Fourier transform does it, I would argue, in the most brain-dead way possible. So let's say that I have two vectors, So here's, I'll draw them for you so you have something to look at that isn't your instructor. So here's V and here's W. And I want to know how much V and W have in common. Like, so maybe when they're parallel, they're very similar. When they're perpendicular, they're very different. How would I measure that? Dot products, right? So if I look at V dot W, right, then this number is large, or maybe its absolute value is large, when there's somehow a lot of content that's similar, shared between V and W. Abstractly, that's kind of what's going on. Yeah? So let's say that I want to know how much of a given frequency is in my function f of x. Well, one thing I could do is just operate in a very similar fashion. So let's say that I always get the relationship between frequency and all these things a little bit wrong. But let's say that I have sine of omega x. Right? So this is some function that wiggles with frequency, I guess, this thing divided by 2 pi or something like that. And I want to know how much my signal has in common with this thing, right? Because that's roughly the frequency content. What do? Well, Fourier says I just take the dot product. That's it, right? So in particular, well, I have to define what dot product means because there's a big set of functions out there in the universe. But like, what is a dot product? So over here, v dot w is equal to the sum over I of vi wi, right? But what is a function? Well, a function is an assignment of a value to every possible x. So I want to take the dot product between two functions. Instead of summing, I just replace that with an integral. Right? And in some sense, this is some kind of vague notion of the dot product between my function f of x and a new function which is sine of omega x. Do you guys see that? I can also put cosine there. Right. By the way, the limits of this integral depend on the domain of my problem. So maybe it's like from minus infinity to infinity. Right? So roughly, this thing I can think of as some new function, maybe g of omega, right? So for every omega, right, every frequency, I get some new dot product, right? And that's roughly giving me the amount of this vector, which happens to be function, but whatever, that's hiding inside of my function f of x. That makes sense? By the way, I could do the same thing for cosine here, right? And get a new set of values. Huh? Or if I were lazy, I wanted to be a sloppy mathematician, one way to combine those two things together is to be fancy about it and do something like this, right? So remember that this is cosine plus I times sine. So when I evaluate this integral, I secretly get two values out. This is just mathematical shorthand. There's nothing more than taking dot product with sine and cosine at the same time and getting two numbers. That's all. You don't need to. Complex numbers here don't matter. But that's the basic point, is that the Fourier transform takes as input a function f of x, and outputs a new function g of omega, where for every omega I evaluate this integral, and that's the number I get. And the kind of amazing observation by Fourier is if I do this twice, I get back more or less f of x again. But that doesn't actually matter a whole lot for here. Does that make sense? So that's roughly what the Fourier transform is. And I guess here, instead of omega, by the way, I've used xi because I refused to use the same letter twice in this class by accident. Okay? But that's the basic transformation in the down direction. Right? And then the observation is in the up direction, there's something you can do that goes back. It turns out it's the same thing twice. That part is a little less intuitive. Okay. Let's see some examples of what this looks like pictorially. I stole these slides shamelessly from the old class I used to teach at Stanford, so this won't mean anything to you. This is Pat Hammerhand. He's a graphics professor at Stanford. Also a pretty famous guy, right? He has an Academy Award. But in any event, here's Pat's Fourier transform. It's in two dimensions because now this is f of x comma y, so I need two different components inside of my sine. And the sort of convention in Fourier is to put the zero frequency right in the middle here. So as I move farther and farther out from the center, these are sine waves that wiggle more and more and more. So one thing that I can do, remember that Fourier transform is invertible. Like I can go from this image back to Pat. So one thing, if you take a signal processing class, you'll spend a lot of time doing is like taking this image, computing its Fourier transform, editing it somehow. Fancy word here is filtering, and then putting it back. So for instance, what would happen if I kind of cut out the middle part of this Fourier transform? I just zeroed it out. Colton.
It would be a lot of specks of color.
Yeah, so at that point I've removed the low frequency information. All that's left is the really wiggly stuff. And the image I get is something like this, right? By the way, the lowest frequency information is just the average color of the image. That went away, so now it's kind of centered around black. Yeah, so now we have a high frequency Pat. So similarly, let's say we start with this, and we do the opposite. I zero out everything except in a little core in the middle. Now what do I get? Yeah.
Get all of the low frequency things?
Yeah, so what does low frequency stuff look like?
Like the level of,
Yeah, it's just something blurry, right? And indeed, that's what we get. We get blurry Pat. And of course, you can do more exotic stuff too, like maybe I just take a little annulus around the origin, so medium frequency. And now you can actually roughly see the frequency here of information that we've kept, right? It's like the spacing between the waves. It's a little tricky in 2D. But in any event, this idea of image filtering is what you'll, like if you take a DSP class in the EE side, discrete signal processing, you'll just like spend a whole semester doing stuff like this. Yes?
So the high frequency here are going to differ than those from the side.
Not quite. So a sine can be low frequency or high frequency depending on omega. So remember that the bigger omega is, the faster that this function will wiggle as a function of x. Right? So essentially you can think of distance to the origin here like roughly the size of omega. Right? So the farther I go out, the faster the sine is wiggling, which corresponds to this sort of noisy component of the image, right? Just this like little speckly stuff. Whereas, you know, when the sine is moving slowly, like because omega is small, that's like this blurry part here. Yeah, great question. Any others before we continue our story? We're going to deepen. I'm going to continue digging here. Okay. So, how do we do it? Well, again, here's our function f of x. We want to know how much he has in common with some function. I've managed to change my convention yet again, and by inserting a 2π. But again, we're keeping it schematic today. We have some wiggly function, which I want to know how much it has in common with. So what do? I literally just stick them on top of each other and multiply and integrate, because that's as close as I can get to a dot product. And that's exactly what the Fourier transform is. If you want to be fancy about it, here's our notation, right? And essentially, typically you read the definition like what I've shown you in this colored box here. But if you remember what Euler's theorem, e to the I theta is cosine theta plus I sine theta. So I can substitute that expression here. And so if you look at the real part, it's like taking the dot product with cosine. If you take the imaginary part, it's like taking the dot product with sine. So essentially all it's doing is just taking two dot products at once. I really wouldn't worry about the complex aspect of it a whole lot. If you're an electrical engineer, you're probably like rolling in your grave. I don't know why you'd be in your grave right now, but if you were a dead electrical engineer because it's Halloween and you were listening to my lecture, you would be very upset that I'm telling you to ignore the complex part. But in any event, for our purposes, essentially those are just two numbers, both of which tell you something about this particular frequency. Okay, so that's our schematic picture of a Fourier transform. Obviously we are missing a lot of information, like does this integral exist would be the key one that you should be asking yourselves and then checking by cracking open your measure theory textbook. But that aside, now we can go, we can do a little bit of an experiment. Remember, we have this model of sampling, right? Where we're going to take our function, we're going to multiply it by an impulse train, and we're going to, and we can ask a new question, which is, if I take my function and I multiply it by an impulse train, like a little set of samples, what happens to its Fourier transform? Does anybody know? This is a story that I feel like actually gets pretty murky even if you have taken a signal processing class. I feel like they don't usually explain this stuff very well. So it's my turn to do the same thing. Okay, so what happens, which is kind of amazing, we're going to see a picture of it, like we're going to do a computational experiment. Actually, it's a total lie. I know what the picture looks like and I drew it in PowerPoint, but you could have done it computationally. It turns out that what happens is you get a function down here that looks like taking your original Fourier transform, tiling it a bunch of times, and summing them all together. This is super counterintuitive and weird. Like, what the heck? Like, why did that happen? Now, phenomenologically, like maybe it makes some sense because I'm multiplying by sine, and sine repeats a lot. Somehow I'm seeing repeats here. That's not much of an explanation, though. Now let's do a different experiment, right? Because we're trying to understand what's going on. I'm going to take my samples and say, well, what if I sampled my function better? I move them closer to each other. What do you think will happen to these bumpy things? Move closer together. How many of them will move closer together? About half of the people that I'm guessing are going to vote. Any other guesses? I'll give you one additional hint. Let's say that I took the limit here and I pushed them all on top of each other so that I basically recover my original function. Well, then I would expect these to actually go away. So rather than moving closer together, actually the counterintuitive thing is they move farther apart. So the closer I sample my function, the farther apart the repeats are in the Fourier transform. You're not supposed to understand this right now. This is supposed to be just a phenomenological picture that we're going to try and explain. Yeah?
Is it though because when you have the delta functions, it just needs, they're so sharp that it essentially needs to like have high frequency waves counter each other out everywhere else?
Maybe. I'd have to think about that one. That could be an explanation, but let's think about some others. Okay. So here's a picture that I think it sort of explains what's going on. Let's say that I have a wave. And in particular, I sample it at 2 points where my wave equals 0. And I want to explain that information. So in other words, I multiply by my impulse train, and what I got was 0, 0, 0, 0, 0, 0, 0. And I want to explain that with just like a single frequency. Well, it turns out there are actually many explanations. Do you see that? Because it could be that it's just the 0 function. That would be the simplest explanation. A different would be that I stuck 1 wiggle of sine. A third would be 2 wiggles of sine. And all of these are different explanations of that same impulse train. Okay? Because I have no information what happens in the inside of the interval. So take a look at what's happening in this schematic here. I multiply here. I've thrown away all information in between here. So suddenly, there are all these higher frequency things that explain my data just as well as the original signal that I had. Right? Because this would be like the 2 wiggles, the 3 wiggles, the 4 wiggles, all of which are exactly indistinguishable from the original signal after I multiply by this impulse train. And intuitively, that's what's going on. Here's another visualization. So if you're taking a physics class and they talk about what standing waves and all that good stuff, so like maybe you have a piece of string and you pluck it and it vibrates. Then of course, when a string vibrates, you actually see the superposition of a lot of different frequencies, right? Like all of these obey Dirichlet boundary. All of these are glued at the end points at 0, but there's different sort of frequencies that you can glue in between them, all of which are nice sine waves and are indistinguishable from one another. And that's the intuition, that when I multiply by that impulse train, I don't know anything about what happens in between these 2 points. Those are my 2 impulse corners. And so what ends up happening in the Fourier transform is you superpose all of these possibilities into one. That's going to be a problem, right? Because I threw away information. As sort of a side note, I know many of you guys play instruments. This is exactly what gets leveraged when you play a lot of string instruments. So in particular, let's say that I have a violin string, or I play cello. I have a cello string here. It's in my office right now. And I put my finger very lightly at this point. And now I drive my bow along the string. What's going to happen? Will I observe this frequency? No, right? Because it wants to vibrate this way, and my finger got in the way. Yeah? Similarly, will I observe the frequency at the top? No. So this is the first one that I hear. So let's actually listen to what this sounds like. By the way, here's a notation of what this sounds like. So here, if you're a musician, what this is saying is clamp your finger down at the black note and then place a second finger at the white note, but only lightly, just enough to dampen the frequencies, but not enough to like put a new endpoint on your string. So right, so here's a really famous little violin passage that uses this effect. Okay, not that part. All right, so what's going on? Is this the normal violin sound? It's really, really high, right? And why is that? What did the Sarasate/Bizet do here? That's what a normal violin sounds like. Okay. What is this effect? It's related to overtones, for sure. In particular, what the violinist has done is they've just lightly, so they're playing the tune with one finger, and then they're lightly placing their finger on a second pitch, which is throwing away all the low frequencies, and what's left are just those really, really high pitches. And so this is actually a technique that musicians leverage to play really, really high notes on their instruments. This shows up all over the place. Another famous one that I found on Spotify before class, it's from Shostakovich. So this is on the cello. If you've ever played cello, this is a really famous audition piece. I have nightmares about this from college. This is the end of my music degree. But in any event, yeah, so that's the sort of effect that you get. And it's just this Fourier trick of dampening out low frequencies by putting your finger right at a node of that vibration. On the other hand, you're also removing energy from that vibration, so it tends to be a little bit quieter and hurt your thumb a lot. Okay, right, so computer graphics somehow has the opposite problem from what I don't know if you call it a problem, but like what's going on in this violin piece, right? Namely, we're not observing really high frequencies. Instead, what we're seeing are false low frequencies. And so now the question is, can we explain that behavior using the same machinery? And of course the answer is yes. So here's how to do it. What would the Fourier transform of this brick wall roughly look like? Yeah.
Like very high frequency.
Yeah, so let's do this in 1D. So let's say my bricks are some spacing apart. Here's the line, here's my spacing, whatever. So, my Fourier transform probably has some information at the low frequencies, but then let's say this is roughly 1 over the width of a brick. And then probably my Fourier transform suddenly has some interesting information here. Right? Because this is roughly the pattern at which my image is repeating. I told you today's going to be schematic. We're not doing real math. So what happens when I multiply this guy by the impulse train? Well, now I take this thing. It's not centered at the origin, but that's OK. I take him and I start tiling him. And in particular, right, so maybe I get a tile here. And I get a tile here. What went wrong? This is a lower frequency than the repetition of the bricks. So what does this mean? That means in my reconstructed signal, I have a lower frequency thing than what I had originally. That's exactly what you're seeing in this image. This is a low frequency pattern, which is happening because you took high frequency samples between the bricks. Right? And that's exactly what a moiré pattern is. A different way to view this is that it's irrecoverable mixing. In other words, these Fourier transforms have interesting information in their tails, and now when I start repeating them like that, the tails get mixed together and I can't undo it. And that's what's going on in this phenomenon. All right, so let's continue to deepen our pictorial picture of anti-aliasing a little bit. And you could ask a different question, right? So now we've identified, the first step is emitting. We've identified our problem. Now the next question is how do we fix it? So in order to think about that question, one question you might ask is like, when is this not a problem? Like, is there ever a scenario where you actually can reconstruct your signal exactly? And the answer is yes, at least in theory. So let's construct that. In particular, never mind what our function is. We're in purple side. Notice I've been consistent about colors. The Fourier transforms are purple today. The P stands for Fourier. Right, so what happened is that the tails interacted. So maybe the scenario where I can actually fix this bug after I sample looks something like this, right? So now I have a function where his Fourier transform, if you want to use a fancy math term, is compactly supported. That just means it's 0 outside of some interval. So now, by the way, what does this mean? In some sense, this picture that I've drawn is telling you that your function has no high frequency information, it's just low frequencies, which intuitively makes sense because that's sort of the scenario where you expect to do okay with reconstruction. So now let's say that I sample this image, whatever it is on the green side. Right, there's our intuition. What's gonna happen? By the way, one vocabulary word. We're gonna call this the bandwidth. It's the width of our signal. I should look at my slides before talking. What happens when I sample? Well, this thing repeats. Let's say I sample really, really densely. Yeah.
You get a lot of the peaks, but they don't really cross over.
They don't touch each other. That's exactly right. They all don't interact. Moreover, if I knew the spacing between these objects, at least in the Fourier domain, I could recover the original Fourier transform just by zeroing out all this other stuff. I didn't lose any information when I repeated this signal over and over and over again. Does that make sense? This is a pictorial picture, and we're in kind of an abstract domain because we're talking in the frequency side. The question is, well, what does that mean in the signal side, right? Like, what does that mean about our rendered image, right? And that's the sort of question we have to answer. So first, let's add a vocabulary word. Interestingly, I just got an email this morning from somebody interested in our work on political redistricting who proposed using this in that domain, which was a surprise. But in any event, the term we're going to introduce is Nyquist rate. How many of us have heard somebody throw this around before? Like you're sitting at a bar, somebody's talking about Nyquist rates. You're going to the wrong bars. Okay, so the idea of the Nyquist rate is as follows. If I have my original signal here, and I sample him or her in a sense that is like I still sample that in a really, really wide set of samples, I could still manage to do it in a way that is destructive, right? Like if the repeating pattern is such that these things overlap, then I'm host, right? So the Nyquist rate is the minimum sampling rate, in other words, the minimum spacing between samples that I need to make sure that when I take this band-limited signal, in other words, this thing that's 0 outside of a band, that when I repeat it, they don't overlap. Yeah? And in fact, one thing you can show is that it is exactly 2 times the bandwidth. In other words, that width of that hump. And this makes perfect sense with the schematic that we drew. Remember that we sort of drew this picture and we said, well, if I can squeeze 2 wiggles inside of the spacing between 2 samples, there's just no way I'm going to be able to recover that. That's exactly what the sort of Nyquist rate is telling me. So here's our schematic again. So let's say that I sample my image, so now its Fourier transform is this big repeated thing, and I want to reconstruct. What could I do? I could take my samples, convert it to the Fourier domain, multiply that by a function which is 1 inside of just that middle band, and then 0 everywhere else, and then take the Fourier transform again, and I got back my original signal. Yeah? And so the question is like, okay, well, what does that mean in the spatial domain? Like, what is that actually telling me about my image? Incidentally, one thing you might have heard of, and then I'll shut up. I like the math. This is fun. This is much more interesting than like textures and materials. Okay, so let's say that I have. Oh, right. So has any of you guys heard of the Heisenberg uncertainty principle? Probably not used to thinking about that in the graphics context. The Heisenberg uncertainty principle is actually a theorem about Fourier transforms. And what it tells you is that if you have a compactly supported Fourier transform, then the original signal cannot be compactly supported. That's going to be a problem for graphics because our images tend to stop. And that's going to be what goes wrong between this theoretical picture and practice. But I digress. Okay, so we're going to make use of one additional fact about Fourier transforms you might have seen before, which is that multiplication of 2 things in the Fourier domain corresponds to convolution in the original domain. So what's convolution? First of all, let's start there. So if I have 2 functions, I convolve them. Here's our little schematic. So if I convolve a function against a rectangle function, then what I do is I generate a new function by dragging the red function along the x-axis, multiplying the 2 together and integrating. Right. So this generates the black function here. Right. So for every point x, I recenter my red function there, and then I take the dot product. And that's what's going to give me the convolution between the red and the blue. Okay? We're not even going to bother writing down the formula because, again, we're just drawing pictures today. And so the big point here is that I have f times g in the Fourier domain. Then I have f convolved with g in the original domain. Right. So that's our basic theory. So remember, what did I do to reconstruct? By the way, this is the most abstract little part of our lecture. So if we lose you a little bit, that's okay. We're going to come back in a second. So what did I do to reconstruct in the Fourier domain? I took 2 signals and I multiplied them together. Right? I had the Fourier transform of my sampled guy. That gave me this repeated function. And then I multiplied it by a function which is just 1 inside of a box and 0 outside of a box. Yeah? The thing's called rect. So what I need to do, in order to understand what happened in the original domain instead of frequency, is take the Fourier transform of that box. Yeah, your question, or you're just anticipating what's next? All right, what's next?
so then that means you're convolving with a uniform like box, which is a box layer.
That's not quite right, actually. So remember, we're multiplying a box and the Fourier transform of my sampled thing in the Fourier domain. This means I need to convolve in the original domain, not the box, but the Fourier transform of a box, which is not quite the same thing. Anybody know what that function is called? Not a Gaussian. It's that's interesting. You guys are at MIT. This is called a sinc, which roughly looks like I guess cosine of x divided by x, right? So it kind of looks like cosine, but it shrinks as you get farther and farther out. And this object is the Fourier transform of a box. So this actually completes our story. So let's sketch out our schematic. So now we have 2 parallel universes, kind of like a Romeo and Juliet situation. We have the spatial domain upstairs, right? This green function, which is like the light in the universe that I wish I could sample on my laptop. Down here we have its frequency domain. And in our ideal world where we can actually sample and then reconstruct and make no mistake at all, here's how we could do it. is if I have a spatial function which is band limited, in other words, the frequency component is 0 outside of some region, then what do? I sample below or above the Nyquist rate, meaning that I replace my green function with these red things which were remarkably difficult to draw in PowerPoint. And we know downstairs, and this is just a conceptual picture, right? Like we don't actually compute the frequency domain. It's just in the back of our head. When we did this here, down here, that corresponded to taking our original Fourier transform and then just tiling it at a frequency which is roughly 1 over the spacing between these things here. So that was sampling. Then for reconstruction, what are we given? Well, we're actually given just this function. We're not given the green one. So if we want to reconstruct it, in addition to that, we know the spacing between these center points. In other words, we know the frequency at which you sampled. What can we do? Well, downstairs, we can multiply by this rect function, which upstairs means convolving the red samples against sync. Or in other words, just taking a copy of sync and tiling it at each of these samples scaled by the height of the arrow. And when you add them all together, one thing you can prove is that you get the green function back exactly. You made 0 mistakes in this special case, which never exists in the real universe, where you have a band limited signal, and moreover, you know the precise spacing and the band limit that you need. Okay? In other words, we didn't make any approximation. And that's our nice schematic picture. Here's the big problem, is that like this never happens in real life. Practical signals don't have finite bandwidth. It turns out there's a lot of light in the world, and if I keep looking, I'm going to see more. And moreover, there's infinitely high frequency information, like these chairs in this room, which are constantly bugging my eyes, have very high frequency stuff in the fabric. And indeed, this is exactly the Heisenberg uncertainty principle, is that like, you can't have a signal which is simultaneously uninteresting in space and in frequency. That just doesn't happen. And that's what you would need in order for this whole picture to work out. Which makes sense, because we don't have perfect displays, right? Like we know that something has to go wrong. And so the question is well, what can we do with this? Well, for one thing, what's the reality is when we do ray tracing, we really do get these red signals. That's exactly what we get. And what this theory is telling us is that the best possible way we can reconstruct is to use the sync function. Like I might as well color my little pixel by convolving against that thing. And if I get lucky and the universe that I'm trying to render only has low frequency stuff, then I'll do a really, really good job when I display. When it doesn't, this is just an approximation, but that's sort of okay. That's as good as we could do, because we've thrown away high frequency information. Even that's a little bit tricky, because let's take a look at this sync function for a second. What could go wrong? Like numerically speaking, now we're going to talk algorithms. Well, for one, there's this little lobe down here that's negative. Now, it turns out if you reconstruct a positive function using this thing, if you follow this Nyquist story, that's actually not going to matter. Your reconstructed signal will still be positive. But in the real universe, where you've undersampled, you've made mistakes, you could end up getting negative colors for the light that comes out of your image filter. That's not so great. And so in practice, what people typically do is they take nice approximations of sync that are positive, just because that way you don't run into this issue when you try to reconstruct something that you shouldn't have. Like you have a high frequency signal that you tried to reconstruct with sync, but you used the wrong bandwidth when you did it. Right? Another big issue is that sync is sine of x over x. It goes off to infinity. So what does that mean? That means in order to render my pixel here, I should grab the pixel colors from everything else along the entire row of the image, just with an itty bitty little coefficient, which isn't terribly efficient or probably realistic, right? I mean, this is only the case for this band limited story, which never actually happens in real life. So typically, other than replacing our image, replacing our filter with something positive, we also limit its extent, because otherwise our algorithms would be pretty ridiculously slow. And then finally, a third issue, we're just poking all the holes in our theory before we talk about the practical solutions to this problem, are the real life images have sharp edges. So this Fourier theory is largely relevant to smooth functions, right? And of course, real photographs have sharp things, and there's infinite frequency content that happens right along this line, which is not captured by this theory. So anyway, that's where the rubber hits the road. And now we're going to talk a little bit about what we do in practice. Okay, so in practice, the story is much simpler. So what do? Well, we already talked about the simplest way to anti-alias By the way, if aliasing is the issue we're trying to fix, then anti-aliasing are the algorithms that try to fix it. The basic intuitive solution, which you probably all could have guessed, is simply replacing your pixel color with some average over the center of the pixel. But now, essentially, our entire story here is telling us that we might not want to take an average which just like draws uniformly over that square and averages the color, but rather maybe draws from a larger neighborhood and then weights them by that sinc function centered at the center of the pixel. We did all that work just to reach that sentence. And indeed, actually, one thing you can see, for example, in this image, is that if you do uniform sampling inside of each pixel, notice that the jaggies didn't actually go away. If you look at this sphere here, yeah, it's a little blurrier, but you can still see the same staircasing artifact because we used the wrong filter. But that doesn't stop people. This is probably the most common technique people use because they don't know all the beautiful Fourier theory that you guys all do. And there are many really fast algorithms for doing this. Especially on your graphics card, where we have this giant sledgehammer, which is really good at rendering stuff at the scale of 1 pixel. A very typical thing to do would be to secretly tell your graphics card that your screen is k times larger than it really is, and then render your scene with aliasing at that big scale, and then shrink it down by a factor of k. So now you have, k squared samples per pixel that you actually render, and that's like the world's cheapest anti-aliasing algorithm, right? But of course, the problem with that is that you're basically using uniform weights over that square pixel region, which isn't so great. One way that people fix that is maybe render that larger image, then convolve it against something that looks like sinc, and then downsample it. And indeed, that's a pretty standard trick. So maybe so you can call this a low-pass filter, which is just a fancy phrase for averaging. Right, so here is a typical visualization. So like, remember sinc was that function like that. Here I'm showing you a 2-dimensional filter, which I guess in this case is roughly Gaussian, like it just drops off like 1 over or e to the minus x squared. And you can use these as some kind of weighted average. So you first render this image which is too big, but now instead of just shrinking it by a factor of k, you just choose pixels, you write each pixel in your smaller image as a weighted sum of pixels in the big guy, where the weights roughly look like sinc or some approximation thereof. Techniques in this class generally are called supersampling, which just means more than one sample to generate a pixel color. Okay. There are many different filters that are out there that people use. There's a big trade-off between this, sort of gold standard ideal, which is sinc, but has all these drawbacks of being the extent being as large as the image, only works when theory is nice. And on the other hand, like a square, which is easy to compute, but not particularly nice. The sort of recommended one that I think a lot of people use is a bicubic approximation of sinc. This dates back to 1988. I was, I guess, 1 year old. Probably a little bit less because SIGGRAPH happens in the summer, but in any event, amusingly, how do they approximate this function? Using splines, using exactly the machinery that we know how to do in this class. So anyway, I've put a link here. You can look at the formula they actually give, but it's just some approximation of sinc with the nice property that it cuts off at a particular point, so you don't have to like compute giant integrals over your image. So now let's have a fun show and tell here. Let me turn out the lights because I think these are kind of hard to see. They're also loaded, the slides are on the course website, so if you prefer, you can stick your eyeball into your laptop. So here is our favorite scene with checkerboards going off into the distance. In this case, some balls for added effect. And this is filtered using the box filter, meaning that I render my scene, I think, 2 times as large, and then just shrunk it by a factor of 2. So every pixel is the average of 4 pixel colors in the big guy. And you can see that there is some smoothing, right? I mean, it's certainly not the case that you're just seeing like black and white pixels here. But if you look, there's some aliasing, right? Like here's like kind of a weird wide stripe that happened. There's definitely artifacts. If we switch to that cubic approximation, what do you see happen? Well, if you look closely at the background, you can see that most of that aliasing went away. Can you see anything else in this image, though, that is a little bit incorrect? Yeah.
Noisier?
There's still some noise. Right? And that has to do with the way that they evaluated this particular technique. At the end of the day, you only have a finite number of samples and a finite number of ways that you can query your image. So you have 2 choices, right? You either do it on a regular grid, But then you're always going to be subject to these Fourier issues, and you can see these low frequencies. One way to fix that low frequency is to say, well, now I kind of know that I really want to integrate against sync, and there's nothing in my ray tracer stopping me from sending out a ray at some weird irregular interval. So instead, I'm going to randomly sample and then average those things with weights that look like sync. The reason being that, at the very least, like, yeah, I'll get noise, but that noise isn't coherent. It doesn't look like a Moiré pattern, which is a particularly bad artifact. Like, visually, your brain really wants to find patterns. And even though, like, from a frequency perspective, these two, probably has pretty similar information, that second option is a lot better. Okay, so let me turn on the lights. We'll continue talking about stuff. As usual, I'm carrying on and probably won't reach the end, but that's okay. Right, so summarize a little bit. So uniform supersampling, which is just putting a little grid of colors inside of a pixel, and averaging has the advantage that it does capture high frequencies. In fact, it's very easy to figure out what frequency it captures, right? Because now it's just the spacing between the supersamples. But you can still end up with aliasing artifacts. They're just different aliasing artifacts because now they're the scale of this slightly smaller sample. A different way of understanding that is essentially you're taking the artifacts you already have and just pushing them farther out. Like you're not actually fixing them. You're just moving them to a different piece of the frequency domain. And so a typical fix in practice for this is just say, I'm going to take that noise, that garbage, and replace it with different garbage that my brain is more likely to filter out. This is where your brain becomes part of the algorithm. In particular, I'm going to take all my samples and randomly jitter them just a little bit, and then average those things instead of averaging them on a nice regular grid. Because your brain's really good at detecting regular grids. You're trained for that from birth. And so instead, it's perfectly easy to fix the weights in front of these things so that they still approximate the same convolution filter. That's not so hard. But you're essentially replacing low frequency artifact with high frequency noise. So let's see what that looks like. So I should probably just leave the lights off for most of the lecture today. By the way, I know these are hard to see from the audience. This is just the problem when you talk about anti-aliasing, because we're talking about stuff that happens at the pixel level. Right, so here is our favorite distant checkerboard with no jittering. So you can see that you see these kind of low frequency, like it almost looks like the checkerboard like takes a left turn at some point in the back of the image. When I add a little bit more jittering to the image, it doesn't look any better in the back. It still looks like noise, because I still just have one sample per pixel here, I think. But I think your brain, for example, doesn't perceive that there's like motion in the back. It just perceives noise, which especially in animated content makes a huge difference. And it makes an even bigger difference when you start to introduce additional samples to your image. Again, these slides are online. You can download them and get all in their business, which is what graphics professors do on a day-to-day basis. So I might look forward to my eyes burning out by age 45. Okay, so these issues become particularly subtle in that checkerboard case, because what's happening is as the checkers get more and more distant to the camera, the spacing that you need to sample them becomes different, right? And we sort of talked about this a little bit when we mentioned mipmaps. And indeed, that really is the case. And so this is one of these times where it might be, for example, in the horizontal direction, the sampling you need is different than in the vertical direction in that case, right? Because in the vertical direction, the checkers are compressing. In the horizontal direction, they're not, right? And so people do all kinds of interesting, weird samples to deal with that, specifically in the case of texture maps, right? That very rarely is your texture map just like a square you're going to tile a bunch of times. Usually it's being wrapped around some nice object. Even in this case, by the way, we probably, when we magnify or for display, we probably still use some kind of filter like linearly interpolating. So that's the magnification issue, right? This is the easier one. Now let's talk about minification. This image should be painful for you guys to look at this point. So here's our favorite checkerboard. And here I'm rendering it as it goes away. I maybe stored this checkerboard in a texture map, and my anti-aliasing task might be to choose the right level in my mip map. Remember, my mip map is like a texture shrunk down to different sizes, and maybe when I do that shrinking, I even use some nice sync filter to do it. Yeah? This is this idea of spatial filtering, and the idea is that roughly I need to figure out the extent of this rectangle, but now to make my filtering problem even harder, I've got two rectangles involved. I've got the rectangle on my screen, the sampling between pixels that I'm trying to render, and I also have the sampling between pixels in the texture map. And those are related by a weird nonlinearity because I'm looking at the surface askew. Does that make sense? And so in other words, the filter that I need to convolve against is a sink, right? But the sink is in what space? It's in computer screen space. Yeah? So now if I take a sink distributed set of samples on my computer screen, and I'm looking at a surface like that, and I project them onto the surface, they're not going to trace out a circle anymore, right? They're going to trace out some kind of ellipsoid shape. And that's the actual filter that I have to apply in the texture map domain. And that's where this stuff gets really, really hairy. If you work at like a video game company, then like you should try really hard to avoid working whatever office is implementing these things, because like you're spending your entire life just working out the math of like looking at triangles askew and working out the difference between, you know, pixel grids on your screen and pixel grids in your texture map, which is just a giant headache. So mip-mapping actually won't cut it in that case, right? Because it could be that your mip-map is just done in a nice square way, but the filter you need to convolve against is like some weird rotated ellipse. So for example, well, here's a nice example actually where mip-map is pretty successful. Later on, I think we'll see some where it goes wrong. Right, so here's another, whatever. Right, so then the issue with your MIP level, right, which is which of these resized images you actually want to choose, comes in the relationship between pixels here and pixels up there. Okay. How do we do that? Well, essentially, that relationship is determined by a derivative, right? So what do? Well, I have some dx over here. I have a function that's mapping every location on my screen to a location in 3D space, which is roughly corresponds to a location on my texture map. So what do I need? I need the derivative of that map, which is going to tell me how the spacing of pixels here are related to the spacing of pixels on this curved or pointed away object. Thankfully, it's going to turn out, and this is where we're going to do a little bit of foreshadowing. Later on, we're going to talk about depth buffering on your computer graphics rendering kind of thing, which is that in addition to rendering color, we're also going to render the depth from the camera that every object is. Turns out we can do that in our ray tracer pretty easily, right? We have to compute that t of the intersection. What does that mean? That means secretly we have that depth function here. So it's not so hard to differentiate it. You just subtract adjacent pixel colors and get some rough idea of that Jacobian. And it really does make a difference. So for instance, here is like what happens when you do your MIP mapping, but you do it just in screen space. And you can see that not only does stuff get blurry, I mean, that artifact you're not going to be able to fix. But in addition to that, the lines almost look like they kind of curve into each other. And that's because we're using circular filters, but they really should be kind of ellipsoidal in the texture domain. And so if you go out into industry, this is our part of lecture where we're just talking about stuff at a high level so you're aware that these are issues. I'm obviously not giving you enough detail to implement at home. What you have to do is typically something called elliptical weighted averaging, where here your filtering is happening in texture space, but you want to convolve against something that's isotropic in screen space. Right, so when you push that forward into the texture domain, what you get is this weird ellipsoidal shape. And there's some really nice algorithms out there where you're essentially trying to do that using different kind of MIP maps that are squashed, maybe not just isotropically, but also vertically and sideways and stuff in between. That really does make a big difference. So like on the left-hand side is the elliptically weighted average version of our checkerboard. On the right-hand side is just the isotropic one. And you can see that actually all the way into the distance here, you can see the nice patterns of squares that happen on our checkerboard. Whereas the left-hand side, they just get blurred out. And there's a little bit of a low frequency artifact here. One more fun fact about anti-aliasing, we're done for the day. Can anybody guess where anti-aliasing issues are the most prominent on your computer? At least maybe 10 years ago, I don't know, I guess this stuff changes all the time. But certainly where a lot of effort goes in anti-aliasing? Text. That is exactly right. In particular, when you're using Microsoft Word, you have a huge screen full of letters. Every letter is taking up a pretty small piece of real estate. And what does that mean? That means that these sampling issues are actually really relevant, because essentially the number of pixels being used to display what often can be a pretty complicated little shape, like a letter, is really quite small. So now these kinds of issues with these checkerboards are irrelevant. The issue now is just that text has all these ligatures and serifs and whatever going on. that easily can be quite jagged. Does anybody know what people do to anti-alias text? There's a really cool, I think it's patented by Microsoft, a trick that they use to improve anti-aliasing a bit. It's called TrueType. You've probably seen it in your fonts. So TrueType is a really clever trick. So far, what have we leveraged? We've leveraged a little bit of math, where we talk about Fourier stuff. We leveraged some algorithms, like doubling the size of your image and then shrinking it. We've leveraged a few perceptual tricks, like moving stuff from organized noise to disorganized noise because your brain is better at filtering out the latter. One thing we haven't done is leverage the structure of our display. And that's what happens when we render fonts. So in particular, if you pull up a magnifying glass, microphone probably wouldn't do a whole lot, to a lot of displays. I'm not sure about some of the modern laptop ones, but certainly CRTs and some of the larger monitors, they're not actually color pixels, right? They're just big patterns of RGB, 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 RGB. So what happens in TrueType font, or ClearType font rather, oh, I'm sorry, is that we say, well, actually, that difference, right, there's RGB samples here. It means that I can get 3 times better sampling if I can do stuff at the scale of 1/3 of a pixel instead of the whole thing, right? And so what happens in a ClearType font, which is pretty cool, is that the red, green, and blue channels for your font are actually slightly displaced from one another, so that the whole thing is anti-aliased just in the intensity space along the pixel grid. And this turns out perceptually to make a really big difference. So that's why, especially on like kind of old displays where you can see the pixels, I think it would be pretty hard on modern laptop. If you take your magnifying glass, you zoom into text on your old display, what you'll see is that like, yeah, the text is like fading into the background, which is what should happen when you anti-alias. But you can actually see little patterns of RGB happening there. And this is a really clever combination of a bunch of different things. One is that you're going to have to generate all of these colors anyway in your display. So algorithmically, it's no worse. Thing one. Thing two is you're leveraging the structure of your display. In this case, in order to make ClearType work, you'd better know precisely which of these subpixels are red, green, and blue. Right? Like for instance, if you bought some new screen, like I don't know, some other continent, and like the order of RGB were swapped, then like ClearType fonts would look terrible, right? Because we'd have a little speckle. And it's leveraging a third thing, which we're going to talk about later in this course, which is that your eye is much more sensitive to intensity than it is to color. So even though you have introduced high-frequency noise in the color domain by doing this, you see that? Like the green channel now changes 3 times faster than it used to. Your eye is much more willing to filter that out because your rods and cones are in different proportions. In exchange for anti-aliasing in the brightness channel. And so that's really, all of these things are being combined together to come up with a clever way just to display the fonts on your screen. But of course, that's a really critical use case because it's about 99% of your display at any given time. Okay, so with that, we're done with Fourier stuff. Don't forget your assignment is due tomorrow, I think, which probably means you have a nano quiz on Thursday. And after that, we're going to do real-time graphics, at least in your assignment.